do group problems, and then people would just sit there and not do anything. And I'm like, okay.
Yeah.
But we'll be like, all right, work on this for 10 minutes, and not actually, like everyone would just sit there play.
All right, good afternoon, and you're a new face.
Yes.
Yeah. Did you just add, or were you just not here one day?
Sorry?
Were you the one who just added?
No, I was
Okay, you just not here one day. All right, so still only 4 people, so you're in your group. It's just one giant group because it's such a small class. We did have a 5th student tonight, but they're still in high school, so they won't be here for a few weeks.
Yeah.
But yeah, so it's a class, it's a size of 5, which is awesome.
Good for them.
Loving it.
Yeah.
Right, so at some point, we'll do the group activity, or something to come up and add your name to the sheet and start for the group.
I only got up to 3 times.
And you have to scan that QR code. All right, so we're going to continue. I think we said for what, 45 minutes to 1:45, and then half an hour for the worksheet, then a 10-minute break, and then we'll look at dot product.
So that was matrix.
No, dot product is for vectors. You use a dot product command in Mathematica to do matrix products.
Okay.
But it's not an actual dot product. So what you can do is you can kind of think of matrix multiplication as a dot product, where each entry, so the 1 entry would be like the dot product of the first row of the first matrix, the first column of the second matrix. But it's not really a dot product. That's only for vectors. All right, so we're dealing with space, 3-dimensional coordinate system. We want to find distance from the point 1, 2, 3, or to the point 1, 2, 3 from each of these. Start with the origin. That one's real simple.
Are you talking about for the origin, like all 3 axes?
0, 0, 0.
0, 0, 0, yeah. What do you mean by all 3 axes? You need the coordinates?
Yeah.
Yeah, it's 0, 0, 0.
Oh, okay.
That's always the origin.
Oh. Never mind. I thought you were like saying distance from. Okay. Never mind.
Right? And distance form is the same, except now you have that third coordinate out of right? Well, since it's from the origin to the point, that makes it really easy. Just the square of the sum of the square of the coordinates. 1 and 4 is 5, 5 and 9. You should be able to just pull it.
So I didn't realize it was.
Should the light's green out there?
Oh, yeah.
Yeah, but you can just pull it. For some reason it's already unlocked for us. So you must be the one who just added them.
Yeah, I got it yesterday.
Alright, 1, 4, 5, 5 and 9, 14. This is root 14, right? And we're done. That's the distance. Oh, this glass is too large.
That's how I feel about
We have
it.
to kick someone out.
That's how I feel about the differential equations class. It was such a different.
That's actually a small class.
I know, but like compared to this, it's such a different field.
Yeah,
for sure.
I'm so surprised this class ran.
Yeah.
I'm not complaining.
I wish all classes were this size. That would be great.
You also up your tuition because it's higher.
Oh, well,
Instructors.
yeah.
So,
Well, like,
before they figure that out.
The x-axis, okay, so we're going to draw three-dimensional coordinates. Typically, that's how we represent. Remember, the x comes out at you. Now let's just say maybe there's our point in space. We're trying to find the distance from the x-axis,
So,
but there's an infinite number of distances. The definition for this distance is the shortest distance, or the perpendicular distance, because that will be the shortest distance.
so that the one, or we have to make it the one with the hypotenuse.
Well, the shortest distance, you want the perpendicular distance, right? Well, wouldn't the perpendicular distance occur at x equals 1?
Yeah.
So it would just be 1 minus 1 equals 0, and then you go from the point 1, 0, 0 to that point. That's the actual distance we're finding.
So for distance of the x-axis, it's always.
From any axis to a point, it's defined to be the shortest
Gotcha.
distance,
So
or the
it's-
perpendicular distance.
So it's going to be what the point's at minus 1.
Minus, so no,
Perpendicular.
perpendicular, so in this case, it's kind of hard to, it's really hard to do.
Yeah, I'm trying to.
Right, but- You want to just be perpendicular, so you want to draw a line
Right.
from the x-axis to the point
Mhm.
that forms a right angle with the axis. That's the perpendicular distance.
Okay.
Where does that occur? At 1 on the x-axis. So it's actually the distance from 1, 0, 0 to the point. That's the distance we're finding.
Okay.
Right, it'd be like if you just do 2 dimensions.
Mhm.
Right, you want to find the distance from the x-axis to a point 1, 2.
Right.
You want the perpendicular distance. That would just be the y coordinate because it's only 2 dimensions.
Okay.
Right, but we're in 3 dimensions, so we still have 2 coordinates.
Right.
We still have 2 additional coordinates to work with. Same concept, we're just extending it again. Does that make
I
sense?
see, I see, yeah, that explanation. I see, so you're ignoring whatever point is.
I mean, we're not really ignoring it, but it's 1 minus 1 equals 0.
Right,
Yeah.
right. Okay.
And then the other 2 coordinates would just be 0 because they have to lie on the axis, right?
Yeah.
So it's just that square root. 4 and 9, 13. Or 13 is that distance. I think I'm done, so I already scanned the QR code to do the attendance.
I see what you're saying.
Right, does that make sense? Again, it's hard to draw it out in 3
I
dimensions,
was like,
but the idea is the same.
But no, I get what you're saying, because you have to go away from.
The x-axis.
Away from the x-axis,
Yes.
up from the x-axis.
Well, you're not really going up from the x-axis. It's perpendicular to the x-axis,
Okay.
right? Remember, the x-axis just this direction in and out.
Yeah.
So we're just going away from the
Away from-
x-axis.
Yeah,
Perpendicularly,
right.
right? So it depends on where the point's located, right? So if the point's up here, well, the x-axis extends forever in both directions. Or forever in both directions, right? So you're going along the x-axis.
I see.
So you're just going to the perpendicular point,
Gotcha, I see, because it's a.
which is just, you go to the x-coordinate.
Yeah, it's represented as a line here because it's easiest, but it's up and.
It's not a plane, it is just a line, but the line extends forever
Right,
this way,
right.
right? So obviously I wouldn't be up here, sorry, right?
So you.
Further closer to you, the line, so we'll just move along
Yeah,
like that.
okay.
If you're doing a plane, you will actually
And then
move
to find the
planes
distance, it's how far?
perpendicularly away from the axis.
Okay.
That's the shortest distance, always perpendicular, right? Z-axis, it's the same idea. You want the perpendicular distance from the z-axis to the point, which occurs at z equals 3. So it's the point 0, 0, 3 to 1, 2, 3. Which will wind up just being that, right? you're gonna have 3 minus 3, which is 0. Square root of 5. Another way you could look at it is doing projections. Right, so you could also look at for this one, for instance. Again, if that's our point. Look at the projection of that point on the xy plane. Right, because you're getting rid of the z-axis. Now find the distance of that projection from the origin. Gives you the same thing. Right, so you just go, okay, well, where's the projection? The projection is going to be maybe right there. The projection is the point 1, 2 on the xy plane. Now find the distance from the origin to that point on the xy plane. Right, square root of 1 squared plus 2 squared. It's the same idea.
So I guess the only thing I'm like slightly confused about, the square root of 5, could you draw like a dotted line as to what that distance actually is? Okay. Okay.
That distance.
I see. Okay.
Again, perpendicular. Because you have an infinite number of points you can choose from, but each of those would be longer than the perpendicular distance. Same kind of idea when you're dealing with distance from a plane. You want the shortest distance, or the perpendicular distance from the plane. Well, that would occur if that's the point. Since it's the xy plane, you take its projection on the xy plane, the distance between those 2 points.
Difference?
The distance
Distance.
between those 2 points would be the distance that you're looking for. Isn't that just going to be the height of the point off the plane? Distance is 3. And you have similar arguments if it's like the YZ plane. You just take the projection of the point on the YZ plane and you find the distance between those 2 points. Okay, and then finally, this one doesn't require really any thought. It's just the distance between 2 points in space. It's just straight up the distance formula. Now, the order in which you do the subtraction doesn't matter, right? Because you're squaring. But if we're going to be mathematically correct, the initial point is Q, the terminal point is P. So it should be written that way. Negative 2 squared plus 3 squared plus negative 2 squared. Right, so 4 and 4 is 8, 8 and 9 is 17, so square root of 17 should be our distance. Yes? It's literally the exact same thing as on the plane, we just extend it. Right, that's the only difference when we're dealing with space, is it just adds an extra coordinate.
When you're doing a projection, is it always on the same plane?
Depends, you can find projections on an axis. You can find a projection on any plane. Right, so, depending on what you're looking for.
No.
Right, but in this case, we just wanted the projection onto the xy plane. Right, so you just get rid of the z coordinate. So these 3 points form a triangle in space. Find distance between each pair of points and determine if that triangle is a right triangle. Yeah, that'll work. It's just the length of each line, right? And remember, AB and DA are the same line, so there's only 3 lengths we have to find. So length of AB, just the distance between A and B, right? It doesn't matter which is your initial, which is your terminal. Be what? 1 squared plus 2 squared plus 1 squared? Square root of 6. Length AC, square root 3 squared plus 1 squared plus 1 squared. Square root of 11. And you just need BC. Square root of 17. How do we decide if it's a right triangle? How would you determine if lines are perpendicular in space? You're not incorrect, it's just we don't have the tools right now to do that.
The tan of the length, the inverse tan of the length, to find the angle.
Okay, but you have to find 3 angles and find which one's 90.
Can you use Pythagorean theorem?
Yes, Pythagorean theorem. What does the Pythagorean theorem say?
A squared plus B squared is equal to C squared, so right?
It's actually not what he originally said, but yes.
Yeah.
Sum of the square of the sides is equal to the square of the hypotenuse. And what do we know about the hypotenuse?
It's a long
It has to be the longest length. Of those 3, which one's the longest? So check that sum. Six plus 11, which is 17, which is the square of root 17. Yay. This triangle's right. Write the direct line segment in both component form and as a linear combination of standard unit vectors. Well, standard form is where the initial point, or component form, we want it in standard form where the initial point is the origin. Well, remember, you can move your vector however you want, as long as you do not change length and direction. So the idea here there. And then 7, -2, I don't know. There's PQ. We move P to there. Let's call that P prime. We now need to find a new Q prime so that the length and direction are identical. So again, not drawing the scale, let's say it's that. We know P prime is 0, 0. Well, how did we move, or how did we get to P prime from P?
Just find magnitude.
So I'm just looking at the point.
Did you shelter the coordinates?
How?
So like P went down to the origin and then
How?
so this,
Describe the actual process.
I guess like a translation or
Right.
transformation, yeah, to the, so at point 32, which is 0, 0.
And how would you do that?
To the left 3 and down 2.
Oh, sorry.
Right. We went 3 units to the left and 2 units down. Well, in order to be the exact same direction and length, Q has to do the exact same thing. 3 units to the left and 2 units down. That would be your new Q prime, and the component form would just then be Q prime. And then the component form, we use the point of braces. So 7 has to go 3 units to the left. And Q has to go 2 units down.
So why would the unit vectors keep on the same? Why would the unit vector and,
What do you mean unit vector?
or not, the, like, the PQ vector and
They're identical because they have the same length and same magnitude. Or same length and same direction.
okay. That's it.
Right? That's why whatever you did to P, you had to also do to Q. Well, isn't that just the x coordinate of Q minus the P coordinate, the x coordinate of P? And so I won't be going through that analysis ever again. That's why it is the way it is. And again, I'm just going to break it down, writing into standard, into the standard unit vector notation. I'll only do it once. But the general idea is you want to split this up. Right, you're allowed to do that, sum of vectors. Factor out 4, factor out the -4. There's your I hat, there's your J hat. Right? That's the basic idea. Right. I'll just jump right to 4i minus 4j.
Could you do the last slide? Is the work still on?
This one?
Yeah. Thanks.
And these will be posted as well.
Oh, okay.
These are posted on the site.
Okay,
So
I'll just take it.
you do have access to them at all times. In fact, I'm pretty sure if you open the file, it should actually update while you have it open. Because it syncs automatically. Same thing here, right? Except now it's 3 dimensions. But the idea is exactly the same. You just have one additional coordinate to work with. And in general, even if you go to higher dimensions than 3. The ideas are the same. They just extend to more coordinates. But they're impossible to visualize. What does the 4th dimension look like? I'm talking about spatial. Time is considered to be the 0th dimension. Right? What does the 4th dimension look like? Well, you draw the exact same way. You draw the axis to be perpendicular to the x, y, and z. But you can't visualize how to do that because you can't actually imagine the 4th spatial dimension because you're a 3-dimensional being. And if you believe in string theory, there's 9 spatial dimensions. So our universe is 10 dimensions. 9 spatial and half the time. Which is better than what it used to be. When string theory first came out, it was 26. Thankfully, we've narrowed that down. I think it's called M theory now for the 9 spatial. Q is the terminal point, so it's terminal minus initial. Terminal minus initial. Terminal minus initial. And that is important. It's always terminal minus initial because vectors now have a direction, so the order matters. Two, 2, 0. That would be component form. In terms of the standard unit vectors, you could write that way, and you typically do. There's a problem. If I just gave you that vector, am I dealing with 2 dimensions? Or 3 dimensions? 2. It's ambiguous.
Yeah.
Could be 2, could be 3. I couldn't even be in 5. You don't know.
So you want us to put the 0K?
So you could also just write 0K. Now, if it was 2i plus 2k, that's not ambiguous. That's clearly 3 dimensions.
So specify.
And again, if the I was 0, it'd still be unambiguous. It's 3 dimensions. But with the k being 0, it's kind of ambiguous if you just write 2i plus 2j. Are we working on the plane or in space? There's probably clearly working in space. But if I just give you 2i plus 2j, no other information, you have no idea. Whereas now if I put that 0k, it's not ambiguous anymore. So that's up to you how you want to write it. What are you saying?
Just the, I guess, specify your largest dimension or your highest dimension.
Define what you mean by highest.
Like, if you're like I, J, K, so on, like first, second, third, fourth.
So saying highest is incorrect because who defines what highest is?
Sure.
The standard order, yeah. So Z in this case is the last
Yeah.
component that we typically use, so yeah, we want to specify that one. Time always comes first. We call it the 0th dimension. You don't have to worry about that until you do advanced physics. We actually have to worry about the dimension of time. So
Could you say they're an R3 and then include that way?
you could, that's more writing.
So the component form is the one before you.
In the braces. That's component form, then you have the standard vector. And they're interchangeable. Unit vector in the direction. Now. We don't want to change direction. We're just changing the magnitude. So that's 1. What operation of the 2 that we know can we use that wouldn't change direction? So if you add another vector, is that going to change direction? Could, right? What if you multiply it by a scalar? Would it change its direction? It could. When? If it's a negative scalar, it would flip the direction. But if you multiply by a positive scalar, it keeps the direction, right? It's just going to either extend it or shrink it. Well, we want it to be unit length. We want its magnitude to be 1. Well, if you multiply anything by its reciprocal, it's 1, right? Find the magnitude of the vector, multiply the vector by 1 over its magnitude. That's how you find the unit vector in the same direction. And remember 2 notations. I'm not going to use the norm bars here. B1 squared plus negative 2 squared plus 2 squared square root, right? That's, oh, that's nice. That's 3, isn't it? So our unit vector in the direction of V is 1/3 times V. And you can always verify by font. In this case, it's actually hard to verify the direction.
So what is dV?
That's the unit vector in the direction of V. Oh. But you can verify that's length 1 very easily. Verifying the direction is going to be a little bit more challenging. You can verify they're in the same direction when you study the dot product.
So could the unit vector always be whatever the
Reciprocal of the magnitude times the vector. Right? Magnitude is always going to be positive. Right? 0 only with the 0 vector. Right? Only the 0 vector has a length of 0. Every other vector has a positive length. So you know that multiplying by its reciprocal is never going to change the direction because it's always positive. Physics! Because why not? Weight of 100 pounds suspended from 2 chains, making angles with the vertical of theta and phi as shown in the figure. We want to find the magnitude of the force applied to each chain if both angles are 60 degrees. In other words, for those who have had kinematics, find the tension in the chains. I think that's what tension is. For right now, I'm going to redraw this. Sorry. Good enough on that work. So I want those 2 angles, actually. I'll just draw that as an imaginary y-axis. So here's typically what we do in physics. Start by drawing what's called, again, if you've had kinematics, you should be familiar with this, a force diagram. We treat your masses as point masses. And in this case, we only have 1. So not only am I going to treat that weight as a point mass, I'm also going to treat it as though it's the origin. There's my point mass. In my imaginary coordinate system.
Sorry, in the Blackboard portal thing, where's the
Course information,
quiz information?
and then you'll see Microsoft Sites. You have to click that link.
Gotcha.
You know how to ask me for that. Well, we know we have this force. Let's call that tension 1. Then we have the other chain, which is exerting a force on the point mass in that direction. That's tension 2. Is that it?
The rate of the mass is going down because of that.
You have a third force due to gravity.
There's at least one force in each force.
Actually, even in space, you won't have that force due to gravity. There is no location in space that has 0 gravity.
Yeah, that's right.
Maybe extremely weak, but it exists. Oh, and by the way, you also have to consider electric forces and magnetic forces. That's, again, more advanced stuff, but yeah,
Yeah, I
there's
was gonna say,
nowhere where there's 0 force.
well, yeah. Because force can't be created.
There's nowhere where you're never going to have any forces acting on an object,
Yeah. Is that,
except in an ideal world. There's also no such thing as a pure vacuum either. By the way, we know what the force due to gravity is.
it's just the,
That's the acceleration due to gravity,
it's just the.
which is what? All right, so that's its magnitude. Force is a vector.
Oh, it's mass times x. Well, maybe it's mass times acceleration, so you can get.
But again, that's, you're right, 100 pounds, its magnitude. I want the vector force, not its magnitude. If you're overthinking it.
It's just.
Right, gravity always, in this case, straight down. It's actually always towards the center,
So then
which would be always perpendicular.
Would this be a, oh wait, no.
We're always straight down, rather, towards the center. That's why it's 0, 1. Actually, technically, it's not like it's negative 100. Because it's going downwards. We don't know T1 and T2. That's what we have to find.
Wouldn't you do some of the forces?
Newton's first law. Because it's not in motion, it's at rest. Object at rest stays at rest unless acted on by an external force. Since it's at rest and it's not moving, the sum of your forces has to be the 0 vector. Or, I'm not gonna do that just yet. But the because I'm gonna write T1 and T2. T1, the x component would be the magnitude of T1 times cosine of the angle. All right, and then y component would be the magnitude times sine.
So,
What's the angle for T2?
30. Oh, no, it's
90.
30 plus. What is it? It's 30 plus 90. So
It's not 30 plus 90.
Would it be like the weight to 30, so 60 plus 30?
The reference angle is 30 degrees, I agree. Yeah, 150. Remember, you want to measure the angle from the positive x-axis.
T1 equal to T2 because
Oh.
They're not equal though, are they?
Okay.
Because they're different directions.
Like, because like we could also, if we're solving like summation of forces equal to 0, we could do like the y direction of the summation of both of those T1 T2 is equal to the.
Remember, we're trying to, I mean, ultimately we're finding magnitudes, I think they asked for, right?
Yeah.
But you have to find the vectors. Because those vectors are not the same, so you can't say T1 equals T2. I do agree the y components are going to equal, but the x coordinates do not.
So why are we worrying with x coordinates if
Which
the
one?
weight's only actually?
That's true. But there's still an x component to the chain, right?
I'm forgetting what I'm doing with this, yeah.
That's right. Okay.
Right, because you don't have just a y direction on the chain. The chain is pulling in both a y and an x.
Yeah.
That's why you have to write it in terms of
Or
vectors.
when you're doing your sum of the forces, you're doing,
I'm doing vectors.
it's the total.
Yeah.
It's the total.
Total sum of all forces.
And because you're working with that's something.
This is ultimately what I'm working with.
Yeah.
Right, actually, I have time. So I'll just give you the general idea. You get a system of equations here. Set your x components equal and your y components equal. And what you actually find, that's not a difficult system to solve. Both tensions are 100 pounds. Again, magnitudes we're dealing with.
With an angle.
Because that's what they're asking for. They're asking for the magnitude in this problem. What you would do if you wanted the actual vectors themselves is then just plug those T1 and T2 into the vector forms to get your x and y components.
So I guess if you're dealing with magnitude, why bother with
I guess that was my question.
vectors?
How do you get the magnitude from the vector?
Wouldn't you just be able to do them in the forces then, not worry about?
Oh, we are, but force is a vector. Force has a direction. Right, so what's the magnitude of T1? We don't know what it is.
It'll be one.
Well, because we just found
Yeah,
it.
yeah.
I followed, but I didn't know.
It's a vector equation now, it's not a normal equation.
Yeah,
Because Newton's laws deals with vectors.
yeah.
That's why you have to look at it as a vector.
Because my initial instinct.
So if we were to add both of those vectors together, we would get 100 pounds upward in 0 degree.
Yeah, when you add the vectors together, it's 100 pounds straight up.
Yeah. So yeah, that's just showing the direction.
Right, but notice the sum of the magnitudes is twice the magnitude of gravity. Which is kind of counterintuitive. You would think it'd be 50 pounds each, because
Right.
you already know the tensions have to be the same. The magnitudes have to be the same.
Well, I mean, they have to be at least bigger than.
Well,
force of gravity.
if you haven't taken physics before, and you just look at this, you would go, oh, well, the sum has to be 100 pounds, and they're equal, so half, 50 and 50. And that's not how physics works. And again, you two are going to have to see me so I can add you into the group. There's just going to be one class group, which is only 5. So work on the worksheet. This is the group assignment. You'll have to turn in 1 copy. Right? 30 minutes, then a 10-minute break. Well, it won't be 30 minutes. It will be more like 25 minutes. So that's going to be what? 2:05?
What's in
No, that'd be 15.
it's 215.
Yeah, 2:15, right? 20 minutes would be 2:10. 2:15, then a 10-minute break, 2:25, and you start dot product.
Yeah, exactly. That's what I'm trying to do.
I hope that you have
Most of the time, I still get information over the summer, like, this summer, so.
That's it. Where you use it,
Basically, like, whatever engineering jobs I take, like, I haven't done anything like specifically yet.
So the dot product. This is also called the scalar product. Because of how it's defined. Dot product of 2 vectors. You just take the product corresponding components and sum them together. That's your dot product. Right, so the dot product always gives you a scalar. Some properties of the dot product is commutative. It's a, social, it doesn't make sense. Distributes across addition. This is known as the associative property. And what it says is if you have the dot product of vectors that are scalar multiples, where you multiply the scalars doesn't matter. This one's very useful. Any vector dot itself is just the square of its magnitude. So there's a relationship between the dot product and the angle between the vectors. U dot v is the magnitude of u times magnitude of v times cosine of the angle between them.
If it's not bolded, it's also the magnitude, right?
Yes. Now, angle between 2 vectors. What do you think the range of that angle is going to be? And so what are the possible values of angles between them 2 vectors?
0 to 180, right?
Give it to me in radians.
0 to 5.
0 pi. Right, the reason, right, we agree 0, same direction. 180, they're the opposite direction. right? So you have something like this, right? But now if we go like this, we actually take that inner angle, which lies between 0 and 180. Orthogonal if and only if their dot product is 0. Right? Because clearly the magnitudes aren't going to be 0. So the only way the dot product is 0 is if cosine is 0, and that occurs at pi over 2, which is a right angle. Orthogonal is just a fancy way of saying perpendicular. Right? When we deal with vectors, we call it orthogonal. When you're dealing with planes, you say it's normal.
Normal if it's perpendicular?
Typically that's when you're dealing with a plane. Right? So if a vector is perpendicular to a plane, we actually would say the vector is normal to the plane. And we say perpendicular for just lines. But they're all the same thing. Angles formed by a non-zero vector with the coordinate axes are called your direction angles, and the cosine of those angles are the direction cosines. Right? What we generally do is we say that alpha is the angle formed with the x-axis, beta is with the y, and gamma is with the z. Vector projection V on the U, vector that has the same initial point as both U and V, and the same direction as U. The length of this vector is called the scalar projection of V on the U. And so that red vector is the projection of V onto U. Again, full derivation is located in the lecture videos. Projection of V onto U, U dot V over U squared, magnitude of U squared, times U. Oh, sorry, usually U on the V. Sorry for that. And obviously its magnitude.
What's calm?
Yeah, I was curious.
That is component to represent the scalar projection. Right, because you can always decompose a vector into what's known as a parallel component to a vector and a perpendicular component to a vector. So that's where the comp comes from. It's the component of V in the U direction. Work. Several instances for work, right? In Calc 2, you studied single dimension, right? Moving along a line. Two scenarios there. The force is constant, or the force is variable. Right? Specifically, it has to be variable with respect to distance. X usually is what you work with, or Y if you're doing gravity. You also should have looked at, oh yeah, and if it was variable, it was an interval, right? Well, force isn't a scalar though. Force is constant, or is a vector, and so is distance. Yeah, position vector, right? So in that case, if the force vector is constant, and it's going along a straight line from P to Q, then it's just their dot product. F dot your position vector. Your force vector dotted with your position vector. Well, what if force is variable? Oh dear. To get an integral. If it's still a straight line that's going along, well, it's not too terrible. What if it's not a straight line? And I have a path integral. We will also examine that at the end of the semester. We'll look at line integrals and work. Right, generally, when you do a line integral, you're actually looking at it going through a force field, not just a force vector. It's only the difference between a vector and a field. Vector is single variate, typically T. Force field is multivariate. Right, okay, good. Want to resolve this vector into parallel and perpendicular components with respect to the vector B. The parallel component. Will be the projection of A onto B. And we have the formula for a projection. That should be B dotted with A over B squared times B. Dot product is commutative, so the order in which you do that doesn't matter. Mathematically, it would be B dot A using the formula, but it doesn't matter. And remember, you can use the standard unit vectors or component form interchangeably. The 3, 1 dotted with 4, 3 over magnitude 4, 3 squared times 4, 3. No, there should be 3 1s. Sorry, I was using A, not B. Well, dot product. Sum of the products. 3 times 4. 1 times 3. So I'm going to write it out. That way, right now, it would wind up being 12 and 3, which is 15. So we'll do that in the next step. Magnitude squared. Three squared plus 1 squared, and that whole thing is times 3, 1. 15/10, which is unacceptable. 3/2. 3/1. Halves, 3/2. But you typically want to keep it in the same form as what was given. Nine halves I plus 3/2 J. That is our parallel component. I want to say, yeah, it is a parallel component. Perpendicular component. There are actually two ways to do it. I don't recall the formula off the top of my head because it's generally easier just to do this. A has to be the sum of the two components. That means that the perpendicular component is just A minus the parallel component. We just found the parallel component. Generally speaking, that's the easier way to do it. The only time you use the formula is if you don't need to find the parallel component. And we will actually examine that when we look at motion in space. A was 4/3. And that's the parallel component. 4 minus 9/2. Oh, how dare you making us deal with fractions.
-1/2.
In which case I argue, at least they're simple fractions. 3 minus 3/2.
I'm a little confused. Is it, are we subtracting with the scalar, with the vectors? We are,
It's vector A minus the parallel component.
to find the perpendicular one.
3x.
And then just stick with convention, -1/2 I. That's 3x J. And there's your perpendicular component. Right, or your orthogonal component, if you will. So, yeah, real simple. This is like, when do you first do arithmetic? So you come out of the womb? No, that's when you do fractions. Arithmetic is like prenatal. Alright, so this is basically just all of your primary stuff. I find this first stuff so boring. I hate vectors. They're too boring. Find work done moving object along the vector 3i plus 4j if the force applied is 2i plus j. This one's going to be really challenging. So work, it's important to note, is not a vector. Work is a scalar. What's the SI units for work?
Joules.
Joules. The joule. Oh. What other quantity has joule as its SI unit. One that's used way more often. Energy. Work is energy. It's just the energy required to perform the task. We prove conservation of energy at the end of the semester too, by the way. Yeah, that's something to look forward to. Of course, conservation of energy only works if you're in what's known as a conservative force field. Otherwise, energy is not conserved and it only deals with closed systems.
What do you mean by a force field?
We'll study that. We haven't gotten to it yet. The system has to be closed. Otherwise, energy is not conserved. The perfect example of that is you're driving. You have kinetic energy, right? Slam on the brakes. Your kinetic energy drops. Where did that energy go? Well, heat, right? Heat on the brake pads, the brakes. But doesn't heat dissipate? If you're only looking at your car, you're losing energy. Energy is not conserved. Because that heat's radiating away.
But if you look at the big,
But the car itself is not a closed system, so you're not violating conservation of energy. The closed system would be the entire universe.
Yeah.
Because you can't even just look at the Earth, because the Earth radiates heat. It also absorbs heat from the sun. But the Earth itself is not a closed system. I mean, even the solar system is not a closed system. Yet the entire universe itself is the closed system. F dot A, and that's not acceleration. That's our position vector. Or it would be 10 and then whatever units happen to be. We're not told units here, so we don't know. I'm on this because I actually have a lot of time. This doesn't take long. What are Newton's 3 laws?
First, second, and third.
What are they? What do they say? Actually, Newton has a lot more laws than that. He also has a law of gravitation.
an object in motion stays in motion unless acted.
Which law is that?
First,
First law, that's only half of it. An object in motion will stay in motion, an object at rest will stay at rest unless acted on by an external force. That is the first law. What is Newton's second law?
Energy cannot be conserved and transferred.
What's on the second law?
So is that-
third, right?
I don't think that's Newton's third law either, because Newton's 3 laws only deals with motion, not energy.
Oh, right, that's,
You're thinking of something else. What is Newton's second law of motion? Essentially, what you stated is essentially conservation of energy.
yeah,
That's essentially conservation of energy principle. So what is Newton's second law of motion? It's his most famous.
A law of gravitation.
That's not a law of motion.
Just something good.
Most famous.
What is it?
Can you give us a hint? Another hint?
Force is mass times acceleration. What is Newton's third law? Well, this is kinematics 101.
That's physics, right?
Kinematics is a subfield of physics. Kinematics is the study of motion.
Oh, for an action, there's an equal and opposite reaction.
Every reaction is an equal and opposite reaction.
Let's go.
Was Newton correct in the second law?
It didn't make no sense. Like,
Is that correct? Is force mass times acceleration?
Is it like just a very simplified version?
because it's supposed to be a OE, right?
Well, that isn't a B. Acceleration is second derivative of position. But is that correct? There is another statement of the law.
I'm guessing no.
Force is the change in momentum with respect to time. That is a restatement. Are they the same?
Yes.
Momentum is mass times velocity.
And,
So the question is,
yeah,
does that equal NA?
Yes.
yeah, because acceleration is also.
You made a fatal flaw. You assumed mass was constant.
Okay, that's.
Mass is not constant.
What?
Mass is a function of speed.
Oh,
That's incredibly arbitrary.
No, it's not.
You're not losing mass right now.
Ever heard of a thing called relativity?
Yeah, but like.
According to special relativity, mass is a function of your speed. The faster you move,
the one
the more mass you have.
no.
But speed is a function of time, which means mass is a function of time. So, no, Newton's wrong.
The faster you move, the more force.
I wouldn't say Newton's wrong.
No, he's wrong.
He's
He's wrong.
wrong. Going to any.
He's wrong. The only reason it works is because we're dealing with sub-light speeds.
Well, yeah. You're not-
But if you're actually now, if you're talking about close to the speed of light, that is completely wrong.
When would that ever be applicable? Why would you?
The Hadron Collider, when you're speeding particles up to close to the speed of light.
Okay. Sure, not in like, in most applications, you're not really.
Right, but we don't care about applications.
So for this
The
specific,
point is, in order for it to actually be correct, it has to always be correct, which it's not.
This is why I'm.
that's why he's like.
This is why. I'm-
So it's not always correct. Force is not always mass times acceleration. It is, however, always change in momentum. So that is the actual correct form. That is change in momentum. Change in momentum with respect to time. P dot, yeah. Newton's law of gravity is also wrong, by the way. It's only correct if you ignore the relativistic effects.
You mean relativity?
Well, so relativity is also actually incorrect. Because relativity doesn't take into account quantum effects.
I've never taken anything from.
But quantum doesn't take into account.
I argue that that doesn't matter.
So that's where string theory comes in. Where string theory puts relativity and quantum together.
It matters like
Yes, it
the
does.
scale, like
Yes, it does.
depending on application.
Describe the universe.
we don't need to.
You need a grand theory of everything. That's called string theory.
No, I don't need to.
That's because you're an engineer.
Yeah, exactly.
That's why physicists don't like engineers.
I don't need to describe the universe. The universe is.
How
I don't need to describe why it is. It's just there.
Say,
He's
He's
already
just
an
like,
engineer.
continues to dig the hole. Getting engineers just a worse and worse name.
Okay. Throw something and have it float, and then we'll talk. Throw something on Earth and have it float.
Well, according to statistical physics, that's actually possible.
Sure, and according to statistical physics, I run into a wall enough times and I clip through it.
Yep. Or you just combust.
That's also.
We're on something that's interesting. It's an interesting outcome. You just burst in flames right now.
I did actually have my students find the specific key I had them find the amount of work needed on the human body to spontaneously combust.
How much
No, if you don't work on the body, it's not spontaneous. Spontaneous
I was
Out of nowhere, each person
I was
does.
more so talking about like how the human
But
approach goes.
it's actually possible for you to just sit there and not do a damn thing, next thing you know you're on fire. That is an outcome.
I was talking about
It's that
how
physics.
the human approach goes.
Or yes, as you said, you just tunnel right through the center of the earth. Quantum tunneling.
Highly.
It's highly unlikely, but the probability is not zero. In fact, there is no event that has a zero probability,
I hope Isaac's one.
according to the laws of physics. It's just probabilities are so small you need to wait around longer than the age of the universe. So we
So
say,
therefore they don't matter.
we just say they're negligible.
Exactly.
Proving my point. But when you're actually doing physics, theoretical physics, you have to take those into account.
Mind you, you said theoretical.
Yeah, well, what do you think my branch was?
Yeah.
Theoretical.
Right.
Which means I don't care about applied. I care about the theory.
I care about that.
You could theoretically, but it's plain right now. That's all I care about,
I hope so.
because it's interesting.
I mean, you can only do applied if there's theory, right? So.
Yeah, that's true. Or this would all be nonsense and we could be proven wrong tomorrow. We could find something that actually just destroys the laws of physics as we know.
Yeah.
And then we correct.
Isn't it like technically anything that's not directly observable is theory?
Well, not necessarily directly observable. You can directly observe gravity, right?
Yeah.
But it's still just a theory. What you're trying to say is you have to be able to directly observe it in every possible scenario
Yeah.
in order for it to be law. We can't. We can only do it on Earth. Right? We assume that the planets orbit the stars because that's what we're observing, but we're observing it from Earth. There actually could be interference that makes it look like that's what it's doing, but it's actually not. We don't know. Oh, and then once you go beyond the singularity of a black hole, all physics just breaks down. That's really cool.
Yeah.
And that's really cool.
That I can.
If you can survive long enough,
Yeah, you know.
and it's really cool.
Yeah, you know.
We don't know. We actually don't know.
I would like to think that you don't.
I would like to think that you do, and it leads you to a different universe with different laws of physics.
That'd be cool.
I mean,
But there's no way to ever know.
There's no
That's-
chance of it.
Like,
that would be
here.
that would be.
It's negligible.
We actually can't say it's negligible. We can't actually calculate that probability because we don't know enough.
Well, isn't it like?
Because all physics breaks down beyond the event horizon,
Because yeah, I was gonna say.
which means all our calculations are meaningless.
Yeah, I was gonna say, isn't it like black holes that are like the main thing of like mass can't be created or destroyed? What happens when you throw something in a black hole?
That's not necessarily mass. You're thinking about information, conservation of information.
It's like an escape, right? Yeah.
So it seems the black hole theory seems to have violated the conservation of information. Right? You throw something into a black hole, you're never getting it out again.
Indeed.
So it seems you've lost that information, but actually, you didn't.
Could be another universe, right? That we don't.
No, I think it has to do with the Hawking radiation, if I remember correctly.
Yeah, because they're there.
Something weird like that, and it's, by the way, permanently pasted on the black hole from our vantage point, right? Once they actually hit the event horizon, so like, you know, I'm gonna pick on you because you're an engineer and just prove my point about years. He irritates me enough, I chuck him into a black hole. Once he hits the event horizon, from our vantage point, he's always there. He doesn't do anything. He's stuck on the event horizon. He's not. Now, from his vantage point, it's going to be something completely different. The current theory is spaghettification.
Oh my god.
He gets torn out the atomic level.
That's the one that I like.
But that's assuming you survive long enough. Because it's also insanely hot.
Yeah.
Right, but we don't know. But from his vantage point, something. From our vantage point,
I just like
he never dies.
I like the visuals.
So there you want immortality, jump into a black hole.
But you could be that.
You're now immortal. Because from everyone else's vantage point, you're always there on the event horizon. You never die. You just stay there for eternity. Because time stops. The time is also a function, by the way. Time is not
I
constant.
say that's delving into more philosophical beliefs of what constitutes death.
No, well, I'm talking about that, yeah. If you're talking about time, I was actually approved mathematically. Time is not a constant. Time is also a function of two things, speed and gravity.
That's why Everest, like top of Everest, using time traveling.
Well, you're technically time traveling right now.
Well, sure.
And that's why GPS has to correct. There's a time correction for GPS.
Isn't it like time space off a single thing?
It's the time correction itself is actually very minuscule. I think it's
Oh yeah.
Less than a nanosecond difference.
Really tiny.
per year or something like that. But time actually moves slower. It moves slower for us here on Earth than it does for the satellite in orbit.
Yeah.
But it's very minuscule. It's less than a nanosecond a year difference.
It's slower on here than it is up there.
It moves slower here.
Okay.
The closer you are to a gravitational object, the slower time goes.
Okay.
So if he's in the black hole, like.
And also, the faster you move, the slower time moves. So the whole concept of Planet of the Apes, that's theoretically possible. Not necessarily the planet is ruled by apes, but the fact that you travel for a year and you come back and thousands of years have passed on Earth. That is theoretically possible.
I think that's the plausible one side.
I think that's called time dilation.
Yes.
So that is all. So there's really nothing constant.
So if he's at,
Except energy. Energy's always constant.
if he's at a black hole, does like time stop for him?
No.
No,
Not
time
But like is the
Time
gravity?
never stops.
Not stop, but like slow down. Like
It will slow down for him, yes. The closer he gets, the slower time will move for him. For us, it seems like time stops because he's now at the event horizon. So for us, it looks like time has stopped. But for him, it doesn't. If he survives long enough to actually be able to look at a clock. I'm sorry.
That's why I would watch in case I fall into the black hole.
You're also assuming that March survives.
You know, I'm conscious enough to be aware, and I'm not like dead.
I like to think that the ending of Interstellar is what
haven't
the
seen
center of a black hole is.
haven't seen Interstellar.
Keep your show up.
Soundtrack,
I have to watch
It's
it.
such a great movie. Just don't watch the first hour or so.
yeah,
Yeah,
that's
sure.
part, right?
Because of the first hour, I saw
That shit.
That's-
First hour. Once you get into the actual space part, that's cool.
Yeah.
I shouldn't speculate. I find theoretical physics interesting. I just don't like the application. That I think is not really.
Yeah, I'm not a huge applied fan. I'm more of a theorist when it comes to the physics. When it comes to the math, I'm more
And that's
one. I
what-
like to see where math
that's
applies.
what we did.
But I like theoretical physics. I was not a lab person. I hated applied physics. I hated applying it. Loved the theory behind it, though. I would be the guy who would go, okay, here, this is theoretically possible, and give it to you. Now prove it, you can do it. Have fun. And I'd walk away. But then you'd come to me and go, couldn't I do this? And I'd say yes or no, and then just get back to
I
you.
mean, it depends on your theory. If your timeline is like this happens and it's going to affect like at least you bet the universe, then it just wouldn't care.
Disney was going to beat that, but hold that.
I don't know. I mean, there's a lot of. There's also a thing that the universe has a bounce and it doesn't actually have like a gap at all. It just all resets. That's a fun one.
Well, the universe itself then dies. It just, well, gets born into a new universe.
But it just does the exact same thing. all over.
Now, I actually subscribe to the peak ring theory,
That one I don't know.
What's that?
that the universe is actually a multiverse, and it's just a bunch of, think of flags waving in the wind. Those are brains. And there's an infinite number of those brains. And a big bang is when the brains collide. And that creates a new universe.
Yeah,
There should not be a simulation yet.
And then each universe has its own physical constants.
you don't believe the simulation thing?
Absolutely.
That's an interesting, that is an
It
interesting
also
theory.
doesn't matter.
I don't really subscribe to that.
It also doesn't matter.
Professor, what's O on that?
So
If it's a simulation, you can't.
So
tell
bad,
it's a
you
simulation right now, doesn't really matter.
No.
Oh, it was the origin.
Oh, okay.
Or
That's why I find
the
it-
origin to human.
So, yeah, so line segment OP would be the vector that has initial point origin and terminal point P, which makes finding its component form very easy.
Okay.
Now, because those vectors are already in standard form. Right, by solving the relation that we were given earlier, you can say that cosine of theta is dot product of the vectors divided by the product of their magnitudes. So the dot product would be what? 2 minus 6 is negative 4, minus 3, negative 7. Okay, 1 squared, so 1 and 4 is 5, 5 and 9 is 14. Times root 4 and 9 is 13. Oh, they both root 14? No, that can't be right. No, they are, okay. Cosine of the angle is negative 1/2, so what's the angle?
Oh, the angle. 90.
Or cosine,
Which is what?
negative one.
Which is negative 1/2, which is what?
180.
2 pi over 3.
2 pi over 3. Remember, radians, unless you're told otherwise.
Is that like the same thing for angles?
Radians are the
No, no.
unit,
Radians is.
is SI. It's SI units. Although, to call it a unit is incorrect. Radian is not an actual unit. Right, so you don't say 2 pi over 3 radians. I mean, you can, but you don't have to. So when you do like radian per second, that's only to make it sound nice. You actually don't need to include the radian because it's not a unit. It'd be per second, right? So you say 2 pi over 3 per second.
No, that's crazy.
That's why people say radians per second. That's kind of why it's there, to make it sound nicer for engineers like him. For physicists, we would ignore the radians because we say, it's not even a unit. Why write it? Waste time. Could be finding out what happens in the center of a black hole. And how long it takes us to write radian.
Nothing you're dead.
We don't do that. I'm going to find a back home and throw it with it just to say.
Okay. Have fun with that.
I'll keep it, I'll make sure that we have cell phones, and just make sure it keeps broadcasting.
But we will use the information.
I can't wait until Voyager crashes into a black hole.
Oh, crashing too.
Well, like, yeah, it won't crash into it. Sucked into it. Gravitate stories.
Find that angle.
I finally gotten the honor of making someone mad enough at me to want me to
Well, it's not necessarily something bad, it's just, I don't know what happens.
It's fair.
And you find it irritating, so you're gonna be my test subject.
No, it's fair.
We have to go into,
I don't know if I know, like, you're just the lazy people are mind of shoving into a black hole, but.
If we're talking about lists, you're not.
Oh, yeah.
oh, yeah.
There was some in that.
Yeah.
My wife has used it on many occasions. Love you, honey. How do we go about finding this angle?
I was thinking wild cosine.
You can, you're still gonna need something.
We need to.
You would need lengths to use log cosines. There's actually an easier way. There's now an easier way. So we're not gonna use log cosines. Dot product of what? Or we're gonna be using dot products, but what are the vectors gonna be? Because remember, you need vectors to take a dot product. Yep. You don't need CD. We're just finding the one angle anyway. So either AC and AB or BA and CA, any combination of those. It's not gonna matter, you're gonna get the same angle. Right, so just treat each of those lines as a directed line segment, as a vector itself. And we're gonna first need AB as a vector. What is AB as a vector? Component form?
0.
What was it?
Yeah.
Oh.
Oh, it's not on my bad. I was thinking down.
One.
3,
Yeah.
-1, 2.
Negative one, negative one,
0.
0.
I don't want to keep wanting to add.
Sorry, you made that too easy. It's because you're an engineer.
Yeah.
That was too easy. It's all in good fun, if you know that.
Yeah. I've been told worse.
Oh, in all seriousness, you are doubly screwed. I was talking to him about it on Monday. You do realize that both mathematicians and physicists hate engineers. And I'm both.
So do architects.
And I'm both a mathematician and physicist. So you're like
Yeah,
doubly screwed.
It's like we're already trying to fight our individual battle against all the other engineering students, and then this.
Viewing is mutual, it's fine.
Yeah, the engineers don't like us very much either.
I work as
But mainly it's because he tells me they're wrong all the time.
I work as a physics teacher. I deal with you guys often. It's fine.
I feel like for engineers, it's more like we're designing for safety, and so long as we hit certain.
You're not designed for safety, you're designed to make money. You don't care about safety.
Well, if you over.
I put you back to the rocket that blew up.
I'll consider this song.
That wasn't engineering. That
Wasn't engineering.
That was an engineering.
That was engineering.
which rocket are you talking about?
The one that blew up because they assumed the units used were the empirical units, not the metric.
No.
I know what you're talking about.
I think it was the Challenger.
Yeah.
I've never heard about that one.
That's crazy.
That was totally wrong.
That was wait, which one was it? Was it the Challenger?
They were amazing.
I don't remember which one it was. I don't know what it was,
But it
but
had the teachers on it.
oh, I don't know.
Oh, that
Is that
the
one
one
standardized?
That one also.
No, they standardized it before, but they just didn't.
Was that the one that was more recent?
Yeah, they just never converted
I
it.
think so.
They assumed it was all empirical.
Okay.
And
Yeah.
then-
So it's
The
not
one that
engineers.
was
What
like.
cost?
I know it's
They did everything correctly. It was empirical units. But
No, bro,
That's
they're
just,
way
okay, I will, like, my grade
So-
with that is that we should just all switch to standardized unit systems.
That's all, no, that's not.
I agree, but it would cost too much money for America to do it at this point.
Well, I mean,
That's a whole different story.
We're, like.
What's AC?
-3, 1, and 1.
We agree?
Yeah.
I do not agree.
Negative one is.
Yeah, it should be -1.
Because they're more.
0 -1. Good. Now it's just right. That's here, right? The dot product should be -4. Length of AB is an easy one, that's just √2, right? Length of AC, √11. That's -4 over √22. There's your angle. Inverse cosine -4 over √22.
Will we ever have to use a calculator to figure it out?
Yes.
We usually do.
If I ask for approximation or decimal approximations are provided within the problem, then you approximate. Otherwise, you leave it in its exact form. Good, just like that, I only have 3 questions left. And I have 20 minutes at the start of the next class to do it, because the last 30 minutes will be the worksheet. So like I said, more than enough time for this one. The dot product is very easy.
We would keep it in that form. Right.
Yeah, unless I ask you to approximate it to a certain number of decimal places.
You have to use a calculator with those, yes.
So we still have the first homework that is due Monday. Now, remember, we will not meet on Monday, so I won't see you again until Wednesday. No, that's a different course, so I'll mention that on Thursday. On Wednesday, when we meet again, we'll finish this up, and it'll be 50 minutes to finish up that product, 20 minutes for the problems, 30 minutes for the worksheet, and then the last 75 minutes, I think it is, will be cross product, we start cross product.
You should check out.
Have a wonderful holiday.
Thank you,
Is
President.
it like,
That's how we got it.
Oh, and 2 of you need to see me so I can add your names.
We have a, I know.
Okay.
Yeah.
Do you like
Oh,
radio
by the
stuff?
way, for the homework, thank you.
What kind of fiction?
Like radio?
Codes and the.
Like basically like,
don't know what that is.
fiction.
You have to buy, it's like $30.
Oh, no.
They give you 2.
No.
Damn, that's where we can